Hi everyone, today we're gonna talk about the curl and divergence. First, let's say the definition here. If we say this operator del is defined like that, then we can say curl f is actually the del operator gradient, like a cross product with f, so that you can calculate it like this. Okay, so maybe you can remember the formula for curl by remember this matrix. Okay, so let's just try to find the curl of this function. So that example 7.1, f is given by x squared y. Okay, so we want to find the curl of f, and we can calculate it like a ijk ddx ddy ddz, and then there would be the coordinates for f to z plus x and then sine xy, right? So you can say the first coordinate is just using this one. First coordinate is dy of sine xy, and then minus ddz of 2z plus x. And then here, the second coordinate is, you can say, is negative ddx sine xy, and then minus ddz of x squared y. And then the third coordinate is just the ddx to z plus x, and then here minus dd y of x squared y. Okay, so that if I calculate the first coordinate, then you can see that it's just a cosine xy, and then you have x, and then here minus 2. And then the second coordinate is cosine xy, and then you have y here, and just a 0. The last coordinate, you have 1 minus x squared. Right, so that actually it is our is our curve, and I think I missed negative sign. Yes, so you can see that here negative, so that I need to say the second coordinate here has a negative sign, so that yes, it is our curve of f. Okay, and let's do one more example. So example 7.2 here. So let's find the curl of f. It is defined ijk, and then ddx, ddy, ddz, and then e to the xy plus z, and then cosine x plus 1. Here I think I have more space, 2ln y squared plus 1, and then plus xz. Okay, so here the first coordinate is dy 2ln y squared plus 1 plus xz, and then minus ddz of cosine x plus 1. The second coordinate is we have negative sign first, and then ddx of 2ln y squared plus 1 plus xz, and then we need to say minus ddz of e to the xy plus z. Okay, and then the third coordinate is ddx of cosine x plus 1 minus ddy of e to the xy plus z. Okay, so if you take a derivative, then the first coordinate should be y squared plus 1 and then 2y, and we had 2 here, and then yes, minus just a 0, and then the second coordinate is, let me see, so you have z minus 1. Okay, the last coordinate is negative sine x, and then minus e to the xy, and we have x. I think also I missed this negative sign here, So that let's just use negative here. So we can say our car is for y over y squared plus 1, and then 1 minus z, and then negative sine x minus x e to the xy. So it is our car of f. Okay, then here example 7.3, we want to find the car of the gradient f. So example 7.3, f be a function in R3 that has continuous second order partial derivatives. So, and gradient f, we have the f dx1 and the f dx2. I think it would be better to use xyz instead of x1, x2, x3, so that because in the example here it says that it has three variables x, y, z. So then let's use x, y, z here also, so that the x, the y, and the z, we want to take a car of the gradient f. So we just calculate it like as we did before, ijk and ddx, ddy, and ddz, and we have df dx, and then df dy, and df dz. Okay, so the first coordinate, if you can see this one, then you can say that the d squared f dy dz, and the minus d squared f y dz, okay, dy dz. And then the second one, we have d squared f, actually we have minus sign here, but yeah, dx dz minus d squared f dz dx, right? And then the third one, we have dx dy, and then df dy dx, right? I think it'll be better to say here dz dy, but since f has a f can be differentiable. Yes, f has continuous second order partial derivatives. It means that yz are the same as zy. Okay, so xz, the order, if we change the order, it has the same value, xy and yx. So that we can say it's just a 0, 0, 0. So when you say this one, we can just say this one when f has a continuous second order. Partial derivatives. Okay, so we know that car of the gradient f is 0. And one thing I want to mention here is f is just an arbitrary function that has continuous second order partial derivatives, so that you can say that always car of gradient f is 0 with this condition. And I think in the lecture we didn't say what the conservative vector field is, but I just want to say conservative vector field is actually the same as the gradient vector field. So that if the given vector field is can be written as the gradient of for some function f, then we say that the vector is a conservative vector field. Or sometimes we just can say that f is a gradient vector field. So the reason why I introduced this concept is we want to think about this example, and we say let f be a conservative vector field, then show that car f is just a 0. So it means that, example 7.4 here, we say that f is a conservative vector field, so we have the condition that there exists some function such that f is the gradient f, right? And we want to show that car f is 0 vector, and you can say that you can replace f as the gradient f, so car of the gradient f. But in the example 7.3, we calculate the curl of a gradient f is just 0, right? So that we can say it is a 0. So this example says that if f is a conservative vector field, then a raised curl of the vector field is just a 0 vector. And if we think about this example again, then it means that if curl f is not 0, negation of our result, so that if curl of f is not 0, then negation of our assumption. So here f is not a conservative vector field. I mean, we can say that if curl is not 0, then f is not a conservative vector field. So that it is useful when we need to solve this example here. So that let's think about the example 7.5 here. So let f be a conservative, and then I show that a vector field f given like x squared y to z plus x and sine xy here is not a conservative. Okay, so when you need to check whether the vector field is a conservative or not, you need to check the curl f, whether it is 0 vector or not. Okay, so that, but in the actually example 7.1, we find the curl of this given vector field, and we have already got curl f was x cosine xy minus 2, and then minus y cosine xy, and 1 minus x squared, right? So it was not 0. It means that, since curl of the vector field is not 0, we can say that f is not a conservative vector field. So we can say, so since curl f is not 0, f is not a conservative vector field. Okay. Using the language you learned in the lecture, maybe you are familiar with this example. So if f is given like this, we want to show that f is not a gradient vector field. Okay, instead of the conservative, I think you are familiar with the gradient vector field. So that we want to show that here the vector is given like that, we want to show it is not a gradient vector field, then actually we need to do the same thing. So that our f is given by e to the xy plus z, and then cosine x plus 1, and then 2 ln y squared plus 1 plus xz. But this one actually we also have already found the curl of f here, because if you find the curl f, we calculated it, and I think it was for y over y squared plus 1 and 1 minus z, and then minus sine x minus x e to the xy. Okay, and this is not 0, so that we can say this f is not a gradient vector field. Okay, and here is an example 7.7, and it's a little bit different, but what you need to do here is, if f is given like that, we want to find the function f satisfying f is equal to gradient f. So let's do it together. So that example 7.7, here f is given like yz plus e to the x, and then xz minus cosine y, and then z plus xy. And what we want to do here is we want to find f satisfying f equal to gradient f. And let's focus on what the gradient f is, and maybe you can say it is partial derivative with respect to each variable. And then since we want to show that f is equal to gradient f, then we can say we want to solve an equation that fx is equal to yz plus e to the x, and then the second coordinate gives fy equal to xz minus cosine y, and fz is z plus xy, z plus xy, yes. So here to get function f, we need to integrate this one first. So that, let's say this is 1, 2, 3, and we want to integrate. First is in first equation, then you will get f of x comma y comma z is xyz, and then you will get e to the x. And then actually you need a constant here, but we just integrated with respect to x, and so there are two more variables. So that instead of the constants, we need to put a function, actually a function of y comma z. Okay, when we integrate the function with respect to one variable, but there are the rest of variables, then we need to plus some function with respect to the rest of variables instead of just the constant. Okay, and then we to use the second equation, we just take a derivative with respect to y, then you will get df dy, and then the right hand side becomes xz, and then plus dz dy, right? And you can compare this one with the second equation, and then the second equation says that df dy is xz minus cosine y, so you can say that yes, then dz dy dg dy is actually negative cosine y, and we just take an integration here. Then g was a function of y comma z, then we just integrate this one with respect to y, so that there is one more variable here. So then it means that after we integrate the right hand side of sine y like that, we need to add another function with respect to z instead of just a constant, because we have one more variable here. So it means that we need to plug in g, y, z, this one, into our f of x comma y, z, so that we have f x, y, z is equal to x, y, z plus e to the x plus sine y plus h of z. Okay, I just replace g of x as g of y comma z. Then we still have h of z, so that we want to find the function, and you can do it by just to take differentiation with respect to z. Then you will get df dz is right hand side becomes xy, and then plus h prime z. Okay, since h has only one variable, we can use this just a differentiation notation. Okay, and we need to compare it with our condition third one. So third one says that fz is actually z plus xy, and then if you compare it, then you can see that h prime z is actually equal to 0. So that if you integrate it, then in this case it has 1/2 z squared plus some constant here. Here actually it is a constant because it is only one variable function, and we just integrate it. Okay, so that now we can say our function f is given by x, y, z, and then e to the x minus sine y, and then instead of h of z, this one, h of z, we can use this one, so that we can say it is plus 1/2 squared plus c. So that is the answer for this one. Yes. So I just want to emphasize that when you want to find the function f, can I use another color? I think here. Yeah. If you want to find function f satisfying the given vector is equal to gradient f, you need to just find the three equations and integrate it, and then take a derivative again to find your f of x comma y, z. And one thing you need to notice here is just remember here, instead of constant, you need to you need to put the functions. Okay, it's not a constant, you need functions here. Okay, so it was the example 7.7, and then And then the divergence. Divergence is defined as the del operator dot product with f, so that it is defined like this. So one main difference with the divergence and the curl is, curl f is vector field, but divergence f is just a scalar, okay, scalar function. So that here, let's find divergence f. You need to take a derivative with respect to x first, then you will get, okay, just to write down the whole things first. So we have x squared y, and then plus d dy, 2z plus x, and then plus dz sine xy. Okay, the first term gives 2xy, and then the second term is just a 0, and then the last term is also 0, so that you will get 2xy. Okay, and then let's do one more example for divergence. You want to just calculate it, so that divergence f is d dx of e to the xy plus z, and then plus d dy of cosine x plus 1, and then plus d dz, and then 2ln y squared plus 1 plus xz. Okay, so you can say it is e to the x, it is not a vector, it's constant. I mean, it's just a scalar value, so that e to the xy and then y, and then the second term is 0, and then the last term you have x. So the divergence is y times e to the xy plus x. Okay, the next example, we want let f be a vector field with second order partial derivatives, and we want to calculate the divergence of curl of f. Okay, the divergence of curl of f. So this example, f is just any vector field, so that let's say f1, f2, f3. Okay, and let's take a call here. That's the ijk, ddx, ddy, ddz, f1, f2, f3. So you have a vector. The first coordinate is df3, dy minus df2, dz, and then the second coordinate is df1, dz minus df3, dx, and then the last coordinate is df2, dx minus df1, dy. Okay, and then we want to take a divergence here, right? Divergence of curl f. Then divergence is to take a partial derivative with respect to x to the first coordinate here, and then plus dy to the second coordinate, and then the third coordinate we take a partial derivative with respect to z. Okay, so it means that you can say df3 dx dy, and then as correct terms f3. Okay, so here you get df3 dy dx, and then f2 you have df2 dx dz, and then f2 here, the plus d squared f2 and dz dx, and then the left terms are d squared f1 dy dz minus d squared f1 dz dy. Okay, so it's just the same things, so we can say it is just a 0. Okay, so here example 7.10, you can say that divergence of curl f is just a 0. Okay, nice. And then it says, so we can say that if divergence of some vector field is not 0, then G cannot be written as the curl. If G can be written as the curl of some vector field, like that, then divergence of G should be divergence of car of F, so that by example 7.10 we can say it is just a 0, right? So that if you have divergence is not 0, then we can say that G cannot be written as the call, okay? So in the example 7.11, f is given like this, and we want to show that f cannot be written as the car of some vectors. So that it means that we just check the car, we need to just check the divergence of the given vector. So that here 7.11. Actually, in the example 7.8, we find that the car of given f was 2xy, right? And it was not 0, so that we defined the divergence, not curve. The divergence f was 2xy and it is not 0, so that we can say f can be written as the car of some vector fields, okay? So that, yes, here we can say this one, f cannot be written as the car of some vector, okay? If it was car of some vector field, then when you take a divergence, we have like this, and we can say that divergence of car of vector field is just a 0, right? It is a contradiction, right? Because our divergence f was 2xy. It is different thing, so it is the contradiction. Okay. Then example 7.12. Is there a vector field f on R3 such that the car f is this one? Okay. Then in the case, suppose there exists car f equal to a to the xy plus cosine x plus 1 to ln x squared y squared plus 1 plus xz. There is a vector field f such that the call is given like that. Then if we take a divergence here, then we can say divergence of car f is divergence of these things. And actually in the example, which one, example 7.9 here, we calculated the divergence was y e to the xy plus x, right? But in the example 7.10, we said that divergence of car f is always 0, right? So you can see that 0 is equal to this one is a contradiction. Okay, it means that there is no function f, vector field f. There is no vector field f satisfying the condition this one. Okay. Okay. Before we talk about example 7.13, I want to just emphasize what's the inputs and outputs of these operators here. We frequently use car, divergence, gradient, and cross product and dot product. So car, when you say car of f, here f is just a vector field, and then this car of f is also a vector field, okay? And then divergence, you need to plug in, a vector field, and then divergence f is just a scalar. It's not a vector, it's just a scalar, okay? And then gradient, you can just apply gradient f to the scalar function, right? Scalar function, and then you will get the vector, okay? Because the gradient f is just a, df dx1, df dx2, df dx3, like that. So your resulting form is just a vector. And then we learned cross products. You take a cross product when there are two vectors, right? The vectors, then you will get a vector. After you do cross product, you will get vector. And then dot products, the main difference is just the output. So that you take a dot product here, then you will get just a number, scalar. Okay. Then let's think about this example. Let's say this F is a scalar field and then G is a vector field. We just want to check whether its expression is meaningful or not. The first one, curl of F. So that curl here, our input should be a vector field. But this F is a scalar field, so that we cannot calculate this one. It is not defined. So that we can say, example 7.13, the first one is meaningless. Okay. And then the second one, gradient F. So that here gradient, we can put the scalar function. Yeah, it's fine. And then you will get vector. Okay, it's meaningful, and we will get vector as the result. Okay. And then the third one here, curl input is vector, yes, and then output would be a vector, so that it is meaningful, and then it is a vector. And then the next one, divergence. Divergence here, you can put the vector, and then you will get scalar, so that you have scalar here. And then the 5 here, okay, first the gradient F. So gradient, you input scalar, right? So it's fine, and then you will get vector. Okay, and this one is a vector, so that input of the curl is vector. Okay, and then the output should be vector, right? Okay, after then we want to take a dot product here, so that dot product two vectors. Okay, and then you will get scalar. And then and then here gradient F. So input is a scalar, so yes, okay, and it is now output is the vector. Okay, and then divergence, we want to take a divergence, so that input is gradient F is a vector. Okay, and then you will get scalar. Okay, the 7 here, curl G is fine, and then you have vector, this is vector, and then curve Z is a vector, so that we can put in the code, so you will get vector. Here, curl of G, so that vector, okay, you get the vector here, you can take a divergence, you will get scalar. And the 9 here, divergence F, you need to put a vector, but it is not a vector, so that it's meaningless. And then 10 here, curl of G. Okay, vector, yes, it's okay, it's a vector. And then gradient F, so the scalar becomes a vector. Okay, scalar becomes a vector, so that we have two vectors, and then we take a cross product, so that we have vector. Yeah, like this you can say which one is meaningful or meaningless, like that, and we need to know the resulting things are vector or scalar, like this. And then the last page is for our homework, and some of you asked some homework problems, so that I just wrote down hint here. So it is homework 13, problem 3. Maybe the function is maybe different, because I used these vector fields as we used it in the examples before. Okay, so here x squared y, and then 2z plus x, and then sine xy. We want to express it as the sum of curl-free vector field and then the divergence-free vector field. I just want to mention that curve-free vector field means if you take a card then with just a zero vector, and then the divergence-free vector field is also the same as, divergence v is just a zero, okay? And so we want to say there are two vectors u and v, and then if we add them, then we will get these x squared y, 2z plus x, and then sine xy, okay? Let's say u is the curve-free vector, and then v is the divergence-free vector. Actually, it'd be better to think about the divergence-free vector because the definition of divergence is simple, more simple than curve definition of curve. So that let's think about the definition. So it is just dv dx dv d. I think it's not a notation. So that let's say v has three coordinates v1, v2, v3, and then divergence v is defined as dv1 dx plus dv2 dy plus dv3 dz, right? And then we want to say it is 0, so that the most easiest way to find the divergence free vector is just make a vector whose first coordinate do not have x term, because we will take a derivative with respect to x here. But in our given vector fields, I think it would be rare to use this one. This one has x squared y, right? And so if we since it has x squared, we just leave this term and we do not take this one. So just to say v1 is just at 0, then it'll be okay. If we take a derivative, then we just get 0 for the first term. And then let's think about the second term here. So that we will take a derivative with respect to y, so that we will take this term here that it doesn't have y, so that even if you take a derivative with respect to y, it is just a 0, right? So that we want to say that the our v1 was 0, and then v2 we want to pick 2z plus x, okay? And then the last one here, we want to take a partial derivative with respect to z, and if you see here, then there is no z terms, so we just want to get these whole things. So then let's say this is sine xy, okay? Then yes, you can check that this our vector is ddx, this one is just at 0, and then ddy of this one is just at 0, and also ddz of this one is 0. So we will get divergence v is 0, right? So that this vector is divergence free vector. And then what is the left term? Here we want to say this vector is u plus v, and we define v like that. Then you can see that u is just a vector. It should be just x squared y and then 0, 0, right? Then if you just add two vectors, then you will get this given vector. And then you can check that this vector is actually car of u equal to 0, okay? So that you can easily check it. Then since car of u is 0, and this vector is car-free vector, so that we can say, yes, this u and v are what we want to find, okay? So then you can say like this. And since you have different vector field, you can do the same things similarly, okay? And then the last example is the problem 5 in the homework 13, okay? I think this calculation is a little bit tricky or complicated, so that I would just want to say, just want to calculate it together here. So that r is x squared plus y squared 1/2, and then f is given by r to the a times minus y plus x, right? And we want to calculate the chord of this f, So that by definition, ijk, ddx, dy, dz, and then you will get here r to the a minus y and r to the a x and then 0, right? Let's calculate it. Then the first coordinate is just the minus ddz of r to the ax, and then the second coordinate is dd, let me see here, ddz of minus r to the ay, okay? And then the third coordinate is ddx, r to the ax, and then minus dy minus r to the ay. Yes. Then let's say that here r is the function of x and y. Okay, so if we take a derivative with respect to z, then it will be just a 0. And then the second term is also 0, and then the last term we need to think about it more. So we just write down like this, plus ddy r to the ay, and we will calculate it. Okay, let's say ddx r to the ax plus dy r to the ay, like this, and then by product rule we can say dr to the a dx times x plus r to the a times dx dx, and then the second term becomes dr to the a dy times y, and then r to the a times dy dy. Okay, so you will get dr to the a dx times x plus r to the a, and then dr to the a dy times y plus r to the a. Okay, and then let's think about how we calculate dr to the a dx. Okay, actually our r was x squared plus y squared and 1/2 here, so it means that r is a function of x and y, right? And then what we want to differentiate it is the function r to the a. Okay, for a while, let's say g of r is r to the a, then what we want to do here is dg dx, right? Because we said g of r looks like this. Okay, so it means that our g is the function of r, right? And that r is the function of x and y. So that dg dx is by chain rule, we can say it is same as dg dr and then gr dx. Okay, so our g was r to the a and then dr dx. So here if we just take a derivative, with respect to r, then you will get a times r to the a minus 1. Okay, and then dr dx, since we have r like this, we just take a derivative, then you will get e to the x squared plus y squared 1/2 2x. Okay, so here r is given like that, so if we take a derivative with respect to x, then you will get this one. Okay, and so here you can say 8 times r to the a minus 1 times 2x, and then 2, and here actually this x squared plus y squared plus and 1/2 is r, right? So you can say that it is 8 times r to the a minus 2 because I cancelled out r, and then x, right? Okay, then let's just plug in here. So we will get 8 times r to the a minus 2 times x, and then we also have x, right? We just write down x squared, and then plus r to the a, and then if you do the same thing, you can also calculate the dr to the a dy, so you will get 8 times r to the a minus 2, and then here y squared plus r to the a. Then it is the same as a times r to the a minus 2 times x squared plus y squared plus r to the a, right? So then just erase it. x squared plus y squared is, if you see the definition of r, then you can say it is r squared, right? So it is 8 times r to the a plus r to the a. So you can say it is a plus 1 times r to the a. Okay? So the car is just the a plus 1 times r to the a in this case. And the second one, using your answer to part 1, find the direction of the color of the vector field with each of the following values of a. So if a is 3, then your car would be 3 plus 1 r to the 3, right? So that is it for oh, okay, I think I didn't write the car. What I just calculate here is, what I calculated here is this one, and it is actually the third coordinate, so that we can say that car of given f is 0, 0, and then a plus 1 r to the a. Okay, then let's think about it, this one again. So if a is 3, then car of f is 0, 0, and then 4 times r to the 3. Okay, this is positive because r is defined as x squared plus y squared. It is always positive thing, so that this whole thing is positive. And we want to just check the direction of the call and enter your answer as a unit vector in the direction. It means that since our car is 0, 0 and positive number, so that the unit vector for that direction is just the z-axis direction, so that you just write down k, right? Then here a is negative 3. In the case, you will get the car is 0, 0 and negative 2 r to the negative 3. And you can see that this whole thing is negative. So that the direction of this one is negative. This direction, it is minus k direction, right? So that you can say it is minus k direction. Okay, and then the first values. And so part 2 tell you about the sign of the circulation around the small circle. Usually we say that if the call is upside, then we say that we have, rotation is counterclockwise, and this direction is actually positive direction. Okay, and if car vector is downwards, then it rotates in clockwise direction. Okay, clockwise direction like this. So in this case, we say that it is negative. So actually, you can just use the, our this direction is positive direction, positive z direction, so that we can say it is positive circulation. So for A, maybe you will get k direction, right? Car F is k direction, so that you can say it is positive circulation, okay? And then here for B, it would be the negative circulation.